Greetings everyone, my name is Daniel Wilson, and I'm a PhD student at Liberty University, studying with the Fluid Research Group under Dr. Wayne Strasser. The title of my talk today is Transonic Core Disrupting Atomization of Banana Puree. So let's get started. First, I want to provide a brief overview of our research. Our objective is to use CFD to characterize the disintegration of banana puree in a novel twin fluid atomizer. You might be asking, why banana puree? It's because it's highly viscous and non-Newtonian. Viscosity drives droplet size, which makes this an interesting case study for atomization. And there are a variety of applications for atomization of highly viscous non-Newtonian fluids. These include manure slurry atomization for energy conversion and fertilizer, which we're working on, gel propellant atomization for aerospace, and also gasification. Through our work, we hope to elucidate mechanisms, instabilities, and droplet size production for atomization of banana puree. On a comical note, I'm going to present the original banana puree production process as demonstrated by a toddler. First, the intrigue. Second, consumption. Third, processing. Fourth, the culmination of delight in the banana. And then losing interest in eating the banana and squeezing, producing shear, and finally, banana puree. On a more serious note, here is our atomizer design, which you can see a diagram of in the top right-hand corner. This is a twin fluid atomizer with steam as the assisting gas and uses an inverted core disrupting design, which is important for a viscous fluid. So steam flows up the middle instead of around the outside of the puree. The steam shear leads to puree instabilities, which in turn leads to droplet formation. And the steam reduces the puree viscosity by transfer of thermal energy, which is helpful for atomization. Our CFD model involves a 90-degree wedge with periodic boundary conditions. And we use a porous media section in the puree annulus to simulate the pressure drop over some length of pipe. Our base mesh is refined twice in the atomization domain to resolve the droplets. And we use the Herschel-Bulkley model for puree viscosity. This is implemented as a user-defined function in ANSYS Fluent. And the Hershey-Bulkley model is, of course, non-Newtonian and shows shear thinning behavior beyond a certain yield stress. Additionally, the steam is modeled as compressible with the ideal gas law. Here's a brief overview of my solution methods in ANSYS Fluent. I'm not going to go into these in detail, but you're welcome to look at those more closely if you would like. What you'll see here is an animation of the banana puree atomization where the surface is colored by viscosity. And what you'll notice is the pulsing nature of this atomization. Interfacial unsteadiness leads to a pulsing flow which amplifies the growth of instabilities and ultimately leads to better atomization. The time scale of these macro puree pulsations is on the order of 0.001 seconds, or every 10 convective times. Here we see a side view of the puree atomization, and we can identify a radial burst event happening in this snapshot in time. What you'll see here is an animation of the side view showing puree atomization. And you'll notice that the periodic pulsing actually involves puree waves forming inside the nozzle. Three general phases are observed with this. First, wave development, then wave collapse, and finally wave rupture or a radial burst. During wave formation, puree continues to stretch downward away from the nozzle until the wave inertia leads to the rupture or the radial bursting. We can look at this pulsing sequence from a different view and identify a similar three phases that are repeated each time this pulsing motion happens. Here you see the first, which is a stretching of the puree down from the nozzle and corresponds to wave development, which we saw on the last slide. And here the puree is colored by strain rate. Second is a holding where the wave is collapsing and the Puree begins to bulge just outside of the nozzle. Third, we see a release, and this corresponds to wave rupture, where we see the disintegration, the radial bursting, and motion outward. And again, each of these are part of the pulsing sequence, which happens regularly every 10 convective times. On the left, you'll see a contour of temperature, and you'll notice that the steam temperature fluctuates periodically through the pulsation sequence due to its compressibility. On the right, you see a contour of Mach number, and you'll notice that this is transonic steam flow, and the steam cooling around the Puree increases its Mach number, so you can see the outline of Puree and droplets. Here we have a contour plot of droplet size shown as solder mean diameter through both space and time in the atomization domain. It's clear that we have spatiotemporally fluctuating droplet sizes, and these periodic fluctuations are moving axially through the domain in a wave pattern. Just in this snapshot, we see 7 repeating units outlined here. Droplet sizes are clearly decreasing in size, moving axially away from the nozzle, which is showing the disintegration process as we would expect. In conclusion, our objective was to use CFD to characterize the disintegration of viscous, non-Newtonian banana puree in a novel twin fluid atomizer. Some of the valuable learning points from our research are that the pulsing sequence occurs every 10 convective times, and we see waves develop, collapse, and rupture to produce radial bursting periodically. Steam temperature fluctuates periodically due to compressibility, and droplet sizes fluctuate spatiotemporally in a wave pattern. We also study mesh independence, but it's not shown here for sake of time. In the future, we'd like to study atomization with fluctuating viscosity in a smart atomization system that we're developing. Thank you so much for your attention. I appreciate you listening to my talk, and I would be happy to answer any questions you have for me. Thank you.